Welcome back, everybody, to INE's CCA Data Center Nexus switching class. In our next section, we're going to talk about port channeling, regular static point-to-point port channeling between the devices, and we're going to talk about some of the caveats that are specific to NXOS that relate to this. We're going to take a look at some examples where we are channeling to the routers and when we're channeling to the end hosts, and then what's the result of the actual traffic flows that are moving through the network. Now, as we know, with port channeling, first off, when we're talking about the different terms, you'll see the terms port channels, ether channel, or NIC teaming pretty much used interchangeably. Anytime also you see 802.3 AD, which is referring to the Link Aggregation Control Protocol, or LACP. This is also referring to port channeling. Now, in any case, regardless of what the term that we're using to talk about it, the goal here is that we're trying to aggregate the bandwidth of multiple physical links between the devices. So, for example, if we had 4 physical 1 gig Ethernet links, we could bind those together with a port channel in order to form a 4 gigabit Ethernet logical link. Now, the key is that once the link is channeled together, and as we saw this in the last section with spanning tree, is that from spanning tree's perspective, we're basically hiding what's going on with the underlying physical topology. So as opposed to 4 individual links where we have 1 of them forwarding and then 3 of them in the blocking state, we're going to have the logical single port channel interface that's going to look like a single interface from the perspective of the spanning tree protocol. So the goal here is that it's going to avoid any type of active standby designs that we have in the network. Really, the goal of the data center is to make sure that we're actively forwarding over all of the links that we have provisioned. So we don't want any of them to be just hot standby links. We want all of them ideally forwarding at the same time. Now, one of the caveats that is not really specific to Nexus, that really has to do with any platform that's doing port channeling, but we will see the end effect of this when we're talking about it within NXOS, is that the data flows that are actually going over the channels, of course, somehow need to be load balanced between the links. And the reason why is that a port channel is technically not, if we were to take 4 physical links and channel them together into a 4 gig port channel link, it's technically not the same as doing something like link fragmentation and interleaving with PPP multi-link. So in reality, it is not 1 link, it's 4 individual links that we would still need to do load balancing across. So a good analogy for this is that when we're doing port channeling and we're adding additional member links, from the perspective of like a highway, it would be the same as adding additional lanes, but not necessarily increasing the speed limit. So the end result of this is going to be that the aggregate of multiple flows in the network will be able to use all the bandwidth of all the member links, but any individual single flow is never going to be able to exceed the bandwidth of 1 individual member. So even in the case of 10 gig channels, if we were to have 2 physical 10 gig Ethernet links that were in a port channel together, it means that any individual flow is not going to be able to exceed 10 gigabits per second. Now, really at that scale, you might assume that, why are we really going to need 10 gigs at all? But really the effect of this is going to be when we look at more flows in the network, and if they don't cleanly fall into the port channeling load balancing mechanism that the platform is using, we can end up in cases where some of the member links are very highly utilized and some of the member links have very low utilization. So we're going to take a look at a quick way that we can solve that and some of the different ways that Nexus, NXOS can deal with that particular problem. So the flow information, so the actual data flows that are going over the port channels, it's going to be load balanced either based on the layer 2 header, layer 3 header, or layer 4 header, depending on what type of traffic that we're actually dealing with. So we have a couple different options here where we could look at the source and destination VLAN, the source destination MAC address, the IP address, the layer 4 header for the TCP and the UDP ports. But the key is that the default mechanism is for IPv4 and IPv6 traffic to only look at the layer 3 header, and in the case of any non-IP traffic, we're only going to be looking at the layer 2 header. So what this means is that with the default mechanisms, we could run into some cases where some of the links some of the member links of the channel are highly utilized, and then some of the member links are very low utilization. And then the solution for this would be to change what is the load balancing method on the port channel in order for us to kind of distribute the load a little bit better between the members. So let's take a look back at our topology diagram here. And again, what we have is a pretty straightforward topology where even in the middle, right now I don't actually have these links provisioned. So let me take these out of the picture even to begin with. So we basically have the case where there's the two fabric extenders that are connecting down to the access layer. And on the access layer, we have the routers here. We also have some servers. So on the 2K1 fabric extender, we have server 1. On 2K2, we have a couple other servers. We have servers 3 and servers 4. And these are dual attached physically with their multiple NIC cards. Okay, additionally, the routers, these actually have multiple attachments as well. So router 3 has two 1 gig links that are going to the fabric extender. Router 2 likewise has two 1 gig links that are going to the fabric extender. Now, we already saw, if we look back at the command line, we already saw the basic configuration of the channeling. There's really nothing very complicated about it, where if we look at the links that we're going from in 7K1-2 down towards one of the 5Ks, and if we show run interface range E to 11 to 12, or just show run interface, so we don't need to say range, we see that both of these links are trunk links. They're both the spanning tree port type network, which means that we're running the bridge assurance feature, and they're both being channeled together in port channel group number 1. And now at the end of this statement, we don't see the mode, either active or passive. This means that we are not using link aggregation control protocol, or LACP, for the negotiation of the link. Most of the time, this is going to be a bad design decision to not use LACP. So there's not many cases where you would not want to run LACP, so you should enable it, typically in the active mode on the links. There are some corner case situations where if your end hosts do not support LACP, that you would need to do channeling statically. I have seen that in the past with some certain vendors' NIC cards or some particular load balancers where either their LACP implementation is not 100% correct or it doesn't properly interoperate. Sometimes you end up in these weird situations where the channel doesn't form with LACP, and then you're going to have to fall back to using just static channeling. Okay, we'll also see a little bit later when we get into some of the more advanced fabric extender designs, and when we get into VPCs, there are cases where you are required to do channeling without LACP, but really any case that you have the option to do LACP, you do want to do that. Okay, so in order to first allow this, we need to go to global config and basically just turn the feature set on. So we need to say feature LACP. And again, this is going to be off on all of the NXOS versions by default. Pretty much all of the features are automatically disabled. Okay, next if we were to go to router 3, and let's look at the show IP interface brief. We have our two 1 gig links, gig 00 and gig 01. And let's revert these back to the default. So let's say default interface gig 00, default interface gig 01. So this is going to remove any of the previous config that I had on there. Do show run interface gig 00, gig 01. Okay, so basically a blank config. Okay, next what I want to do here is to say for the interface range that is gig 0021, I want to put these in a channel group. Okay, this is going to be one of those examples where you cannot run LACP because these particular iOS platforms do not support dynamic channeling. They only support the static channeling. So this means that on the fabric extender, as we're going down to the destination host, we would have to make sure that the channel mode is on, cannot be active or passive. So here on the routers, we simply say channel group 1, or actually not channel group 1, let's see, let's try these individually. Channel group 1. And the router, I think we need to configure the port channel first. So the syntax is a little bit different here. Okay, so then we have the channel group 1. This should be adding both the physical gig links to that channel. Now on the logical port channel interface, this is where we would have any of our like layer 3 config. So our IP address is 10.0.0.3/24. Okay, router 2 is basically going to do the same thing here. So let's say default interface gig 00, default interface gig 01. We create the port channel. Then the member links are going to be assigned to it. Channel group 1. Now the number of the channel here, it is locally significant in this particular case where we are doing just regular static port channeling. Once we start to do this on the Nexus platforms, this does start to become an issue that we need to keep in mind, because we typically are going to have a lot of channels configured on the platform, and you need to keep track of which numbers you have used and which numbers that you have not used. So there's a quick command that you would generally want to reference, which is going to be the show port channel usage. And this tells you just what are the numbers that you have already assigned and what are the numbers that you have not yet assigned. Also note that the warning message here, some of these might be used for SAN port channels for fiber channel. But in this case, we're not doing storage yet, so we don't have to worry about that. All of our Ether channels or port channels here are talking specifically about our Ethernet ports. Okay, so next let's look at the FEX links that are going to go down to the router, where in this case this is E101.1 to 2, 1 to 2. And I want to make sure that these have identical configs, because we cannot channel the interfaces together if they have different access VLAN assignments, if they have different trunking configurations. You'll see that there's a lot of compatibility issues once we start to try to group the links together. We normally would want to basically remove any config on the members, apply the port channel, then reapply any of the options, and then that's going to make sure that it's that's the same between all of them. So here on interface E101.1.1, I'm going to say no speed. Actually, speed I need to leave on there. I'll remove the access VLAN though. No switch port access VLAN 10. Okay, on the second port, E101.1.2, I need to shut this down and say the speed is 1,000. Because again, the FEX cannot do automatic negotiation of the speed there. Then on both of these links, I'm going to shut them down and set the channel group. So channel group, let's say 3 for router 3. In this case, the mode is going to be on because the router does not support LACP. Okay, so again, this is one of those corner case situations that we cannot use LACP. Then at the physical links, we will say no shutdown. Okay, that should cause the logical port channel to come up. Then from here on out, any configuration changes we want to make is going to be on the logical port channel interface. So things like switch port, access VLAN 10, any other things that we want to do, that's going to be done on the port channel link here. Okay, if we now look at the show port-channel summary, this is going to tell us the state of any of the links that we have configured. And there's a couple of fields that we want to take a look at here. And this is going to be pretty similar to regular Catalyst iOS. Okay, first thing I want to know is the channel up or down? So capital U, that's what I want to see. The channel is up. Okay, then I want to see for the member links, what are their states? Ideally, this should be capital P, which means that they are part of the port channel. The S here means that this is a layer 2 switch port. So it's a layer 2 port channel. There are cases where you could configure it as a layer 3 native routed port channel. But in our case here, this is just a layer 2 switch port. It's an access VLAN 10. The protocol is none because we're not running LACP, which again is really just a hardware limitation that we have on the router here. Okay, additionally, just for basic testing before we go any further in the topology, what I'm also going to do on Nexus 5K1 here is to turn on the feature interface VLAN and simply create interface VLAN 10 with an address to make sure that we have basic layer 2 connectivity between the devices. So if the port channel is working, I should now be able to ping 10.0.0.3, which I can. Okay, then likewise, as we configure router 2's channel, we want to make sure, does it have basic connectivity to Nexus 5K2? Then ultimately, we're going to be sending traffic across the entire topology there. So let's do the same thing here over on router 2. So on router 2, if we show run interface range gig 0, 0 to 1, or show run interface, and show run interface port channel 1, we see this is where any of our logical configuration goes, which in this case is just the layer 3 IP address. Then on the switch that it is attached to, which is the FEX attached to Nexus 5K2, we show run interface E102 1 to 2. I want to make sure these configs are the same. So I'm going to go to the link level, say no switch port access VLAN. Then I'm going to create the channel group, so I'll say channel group 2 mode on. Then on interface port channel 2, this is where my switch port access VLAN would go. If we then look at the show port channel summary, okay, again, this is what we want to see, that the channel is up, that the physical links, the members are part of the channel. If we look at the show spanning tree, interface port channel 2, notice that this is an edge port. So because the FEX ports are always going to be our spanning tree edge ports, in this case we are running multiple spanning tree, but if we were running per VLAN spanning tree, it's basically going to be the same thing. Okay, next I want to configure again the feature interface VLAN. And interface VLAN 10, I'll put an IP address here, 10.0.0.52. And I just want to know, can I ping directly to router 2? And then if the rest of the layer 2 network is working, I should be able to ping over to router 3. Okay, this is basically checking my layer 2 trunking that's going throughout the topology. So this is basically telling me there's something wrong in the layer 2 transit between the devices. Now, to simplify the topology, we're going to roll back to the default of spanning tree, which in the last section we configured this as multiple spanning tree. So first I'm going to go to global config and say the spanning tree mode is rapid PVST. That is the default. So this should get rid of any issues that we have with the MST interoperability. And we can see some of those error messages, the log messages that are coming up on the 7Ks. This, again, is because of the root bridge placement. But assuming everyone is running the same spanning tree mode, then we shouldn't have any problems with that. Okay, so let's see now, can I get reachability not only to router 2, but can I get it to router 3 as well? Okay, which I can. So this just tells me some basic information about the state of the network. It means that the FEX between router 3 and Nexus 2K1 is working. The uplinks from the FEX to the parent switch, the layer 2 trunks to the 7K, layer 2 trunks across here, and then down to the final destination. So really just for the static port channeling, there's nothing that's too complicated that goes along with this. So let's now look at adding some of the servers here, where specifically in our physical topology here, this is port E101, because we said this was FEX 101, /1/4 and 5. Then we have server 3 on the other side, which is now going to be E102/1/6 and 7. And then the fourth server, server 4, we have is E102/1/8 to 9. So from the Nexus perspective, there's really no additional special configuration about this. It's just going to look like a normal port channel config. Then we have the option to do either no negotiation or LACP. Really depends on the support of the end host. So let's go down to the first 5K, and let's look at the show run interface E101/1/4 to 5. Right now, these interfaces do not have the same member config, so I want to make sure that that is equal first. So let's say no switch port mode trunk. We'll say that this is going to be channel group 10 mode active. So this means that we are running LACP and we are going to be sending the negotiation frames to them. So we're the one that's in charge of managing and starting the channel. Okay, next on interface port channel 10, we're going to say that this is just an access VLAN, so switch port access VLAN 10. And essentially the same with the other servers on the other side. So when we look at the member links, we simply have these with the channel group command, and then any other config that we put on the port channel interface, this is automatically going to trickle down to the member ports. So just from a management point of view, in general, every time that you make a change to any of the member links of the port channel, you should be making that change on the port channel logical interface, not on the physical link. If there's a case where one member's config does not match another member's config, generally one of them is going to get kicked out of the channel, unless you have the channel mode on, in which case you can actually cause layer 2 loops in the network by misconfiguring your channels. So this is another reason why you would want to run LACP, because it does actively negotiate the link and try to find any problems in the negotiation. And then if there's a mismatch in any of the parameters, it can, on its own, disable the member links, remove them from the channel, and then fall back to normal spanning tree forwarding, where we have active standby as opposed to active-active, which is the goal with our port channeling. So next, let's look on the other 5K. If we show run interface E1021/8 to 9, okay, we see that those member links have the same config. And then same with the 6 to 7. So basically there's no configuration here to start yet. So we'll say that on interfaces E1021/6 to 7, this channel group is, we'll say 30 for server 3. Mode is active. This log message here means that I didn't say feature LACP. Let's go back to the links, turn the channel group on. Then interface E1021/8 to 9, channel group 40, mode active. Okay, both of these port channels now, interface port channel 30 and 40, are going to be in access VLAN 10. So beyond that, there's nothing special about the layer 2 configuration. These are just layer 2 access switch ports. So now let's actually take a look at the end servers and look at what the configuration is going to look like from their point of view. So we looked at this a little bit yesterday. If we go to the first server on the left, server 1, this has a 10 gig converged network adapter. So here we have our two physical links, which are 10 gig 0 and 10 gig 1, these two links. Then we have the team, which is basically the logical port channel interface from the server's perspective. So on the properties here, if we look at our IP config, we're in the same subnet as the other hosts. So ideally, we should just be able to go to the command line, ping to router 3, ping to router 2. Okay, we see just basic connectivity is working on the channel. Okay, also, since we're on the same layer 2 segment, we can see the latency is very, very low. It's less than 1 millisecond. Okay, let's also look at server 3 and then server 4 here. The configuration is going to be logically the same, but it's going to look a little bit different because the application for the NIC cards is different. On the first card, that's an Intel NIC, so the channeling is just done from the Windows network adapter properties. In this case, for servers, or for server 3 here, this is a Broadcom NIC, which has like its own management app. But basically, just what I need to do is to add a new team. So let's delete the old one. And let's also look at the network properties. Okay, so I have two physical links that are going up to the Nexus ports. So I want to create a team. It's going to ask me some basic options like what's the name. I'll say this is team 0. Really what's most important here is what is the team type. So what type of negotiation do I want to do? Some of these NICs will have proprietary ways of doing it. Like in this case, the Broadcom NIC has smart load balancing and failover. What I really want to use is just the open standard version, link aggregation with 802.3 AD, which is LACP. Okay, the physical members are both of these Broadcom NICs. And this other Intel NIC, this is for my out-of-band management. Okay, it also does ask what is the MTU that you want. Most cases for the data center, you want to make sure that you are enabling the jumbo MTUs for your gig E frames. For regular gig E, this is going to be somewhere around 9,000. For your 10 gig cards, some of them can go up as high as 9200 or 9216 in the case of the Nexus. Okay, but otherwise, with the MTU of 1500, you're going to get more overhead when you're actually transferring your layer 3 data. Okay, then if I wanted to do layer 2 trunking here, this would be under VLANs. Okay, so now I should have this, or did that undo it? Actually, that undid it. Let's see, apply, exit. Okay, so it's applying the changes. I should now see in the network properties that there's a new NIC. This is the team 0. This then would be where I want to put my logical config. So let's go to IP. Let's say this is 10.0.0.3, actually 10.0.0.30. 255, 255, 255, 0. Now the fourth server is a VMware virtual machine, which means that the channeling is not going to be controlled by the VMware guest operating system. It would be controlled from the vSphere management in the actual VMware console. From the virtual machines perspective here, when we go to the network properties, they're only going to see basically one NIC card, which is this LAN connection. But this really is the channel group. Okay, so we'll say that this is 10.0.0.40. Okay, now from these end hosts, I should be able to ping 10.0.0.2, 10.0.0.3, 10.0.0.10, 30, and then myself here, I'm 40. Okay, so nothing really complicated is going on with the layer 2 config. It's just everyone is in the same broadcast domain, just a basic access VLAN. Okay, the next thing that I want to talk about here is when we actually look at the traffic flows for the aggregate of flows over the channel links, you will find that with the default load balancing mechanism, you may not actually get the effect of what you think that port channeling would do. Because if I have, in this case, I have 2 physical gig E links, that does not mean that I have a 2 gig port channel. What it actually means is I have 2 1 gig links that are being load balanced between them. So an individual flow would not be able to use 2 gigabits per second. We would only be able to have at a maximum up to 1 gig per flow. Only if we have more than one flow and the load balancing mechanism is correct would we be able to actually send the traffic in a not necessarily equal manner, but in kind of a distributed manner between the physical links. Now, one way that I want to show this here is with a basic application we're going to be using throughout the class for testing basically just different types of network flows. So if we take a look back here at the machine's interface, this is going to be the iPerf application, okay, which is basically just for generating TCP and UDP flows. This specifically is the Java front end, which is the JPerf application. So this is useful just for doing very low-level testing of like your TCP/IP stack to make sure that you are getting like the throughput that you normally would think you would get on your links. Okay, so here this is going to be server 1. I'm going to say that this is the server of the basically listening for the TCP flows. And really the only thing that I want to change here is just that let's say that the output format, let's say the units are in gigabits as opposed to megabits. And let's run the app. Okay, basically what it's going to do is just graph out the utilization of TCP for us. Now from the other servers, let's say we go to server 3. We're going to run the same app, but we're going to run this in client mode. Okay, so we are the client. The server is 10.0.0.10. I want to look at this in gigabits. I want to send a bunch of packets, so let's say 99999. And I'm also going to enable a larger TCP window size and a larger maximum segment size. This is just to make sure that the graph isn't looking at problems with the TCP stack itself. So let's say that the maximum segment size in bytes, assuming that my MTU is going to be 9,000 for the jumbo frames, we're going to say that the maximum segment size is 8960. And we're going to talk about this more within like the scope of QoS, how to do things like enabling jumbo frames, and then what the result of that is going to be in the topology. Okay, so let's run the application. What we should see is that we connect to the server, and if we look at the graph as it starts to run over time, if you can see here, and let me actually make this a little bit bigger here. If we zoom in on this a little bit, you can see that the average is about maybe 80–90% of the link. Of course, this doesn't take into account any of the layer 2 overhead. So if we were to go back to the actual CLI and look at the Nexus, we would be able to see what's like the average utilization on the ports. So if we were to say show interface port channel 10, and if we look at the load, we see right now it says the load interval is being averaged over 300 seconds. Let's go ahead and change this so we can see in a little bit more real time what the utilization is going to be. So let's go to port channel 10 and say that the load interval, counter number 2 here is the default one. Let's say that this is to 30 seconds. We should now see when we look at the port channel, now we have a 30-second rate. Okay, so the 30-second output rate you can see is just under the line rate, so it's just about 1 gig. But the problem is these servers aren't now single gig attached, they're actually dual gig attached. So what we have is that the initiator of the session, which is this guy down here, is sending the TCP flow across the network. It's going to the server. This guy here, server 1, he's got 2 by 10 gigs, so it's definitely not server 1's problem. Server 3 has 2 by 1 gig links, but we can see the individual flow still isn't going above one of the individual members. Now, you would see this problem in your real design if you were to have, let's say, server 3 is running some common application that the rest of the network is accessing. Maybe it's large database synchronization or some sort of large file transfer. If your flows don't fit along with what the load balancing mechanism that the layer 2 switches are using, you may not end up getting your flows assigned to the correct member links, and then you're not going to get anywhere near what the total aggregate of the actual port channels that you're using are. Now again, as we're configuring it now, we only have one flow going through the network. It means that there's one IP address source, one IP address destination, one TCP port source, one TCP port destination. So in any case, we're not going to be able to exceed 1 gig with this flow because we're still subject to what is the physical capability of the underlying member links. Now really the only thing that we could do to try to fix this is to increase the number of flows. So if we were to go back to this server number 3, let's say that we're not going to send just one stream. If you can see, it's kind of small here, but it says right now the parallel streams is 1. Let's say that we send 4 streams. Okay, so now we have 4 streams being sent from the client to the server, and I may need to restart the server. Yeah, usually every time you finish this, you have to stop and restart it. Okay, so the server is listening. The client now connects with 4 streams. And we can see now it says the sum of the flows, if you can see that there, is about 1.7 gigabits per second. So it's definitely more than 1 gig now. if we were to look at the Nexus and then look at the show interface for the port channel and look at the average utilization. So this is getting even closer to the line rate of now the full port channel of the 2 gigs. It's about 1.9 gig, pretty much as good as we can expect from a card like this, the onboard gig NICs. But the key is that just because you have the links channeled together doesn't necessarily mean that your application is going to be able to get that bandwidth. So in a lot of cases, what you would want to do is to go to the switches that are doing the channeling and making sure that their decision of how they're actually load balancing the traffic is going to have enough different fields that they're looking at in layer 2, 3, and 4 that you do get kind of a nice distribution of the traffic. And in most cases, what you would want to do is go to global config and say that the port channel load balancing method is going to be for, and in this case, the 5K, since we're only running, no, that's right, let's see, port channel load balance, source, port channel load balance, Ethernet, source, destination, port. Okay, so this means not only are we taking into account the source MAC address, destination MAC address, source IP address, destination IP address, but also the layer 4 port information. Where in like an application here that we have the TCP generator, each of these flows is going to be using different port numbers because we can't have the same connection from the TCP session based on the same port numbers. So when the server replies, they're going to have some random source port that the server is replying to. So again, this load balancing change, though, this is not going to take effect for current flows. You would have to stop the application and then restart it in order for it to take effect. But it's not something that you would need to reboot the platform in order for it to actually apply. So the 7K pretty much has the same thing. The syntax, I believe, is a little bit different here. If we say the port channel load balance, we would say source dash destination IP plus the layer 4 port. We could also say plus the VLAN. Basically, we're trying to get as much random or pseudo-random information in the flows in order for it to get a better distribution of what the member links that it is actually choosing. So this is definitely important within the scope of the data center environment. You normally are going to have some sort of management application that's keeping track of your link utilization. And if you see on your port channels that some of the members are very low utilization, while some of the other members are very high utilization, usually means it's a problem with the load balancing method that the switches are using. Okay, but again here, the other key point is that regardless, a single flow is not going to be able to exceed the bandwidth of any individual member link, which in most cases is not really a problem because you normally would have multiple flows. But this is, for example, how like your download accelerator works on your like your laptop if you're trying to download like a video off the internet. That by creating multiple TCP streams, when the traffic is actually queued at layer 2 and layer 3, there are different flows from a layer 3 queuing point of view, and then there are different flows from like a port channeling point of view if we're going over either channel in the transit path, and then that's the reason why you're able to get a higher transfer speed when you're sending more than one TCP stream versus just one individual flow. Okay, so we're definitely going to come back to this. We're going to be spending a lot of time on port channeling today, specifically within the scope of virtual port channeling. But I just wanted to get those in channels set up because we're going to be using these as testing for what's going on with the rest of the VPC, the virtual port channels from here on out. Okay, so let's see. We have a couple questions here. Is there any benefit of running LACP versus static, which is going to be error detection on the link and then dynamic allegation of the link, the aggregation of the links, that you can automatically add new links or remove bad links if there's some sort of configuration problem. You cannot do that statically. Okay, so ideally, if you have the option, you do want to run LACP, not do static. There's a question for the order of operations. If we add 2 ports to the channel after the fact, should we mirror the config to them and then add them to the channel group command. Ideally, you want to disable the member links first. So in a real design, when you add members to the channel, you can theoretically add it live, but sometimes it doesn't work out, and you can cause layer 2 loops in the network and then potentially even take that segment of the network down. So ideally, if you need to add links to the channel, you're going to schedule a maintenance window to say, I need to temporarily shut the link down, add the new members to the port channel, bring the links back up, and then they're going to negotiate all of the links together. Why would you not choose the most granular load balancing hashing? I'm not really sure why you would not. The only potential issue would be if the platform gets overwhelmed with making the decision. So if your platform has maybe some sort of CPU limitation on how fast it can do the hashing, as far as I know, Nexus, especially Nexus 7000, does not have that problem. So maybe with 6500, depending on what's the supervisor, what are the particular line cards that you have, you may hit some hardware limitations on what you can or cannot do. But ideally, if you have the most possible fields for your input to load balancing, you're going to end up with a better traffic distribution. Because I'm going to assume that if I look at just my MAC pairs versus my MAC pairs and IP pairs, or MAC pairs, IP pairs, layer 4 pairs, all of that together is going to end up in a better random distribution of what the ultimate traffic flows would be. There's a question on the catalyst. You can typically choose only one type of hashing. It really depends on the particular platform in the version. But the syntax is going to be the same. It's going to be that port channeling load balancing method. There's a question, what stops a platform from doing round robin per packet on the individual links? You theoretically could do per packet load balancing. In a practical application, though, it usually doesn't work out that well because your packets a lot of times will get to the destination out of order, and then you have problems with the actual end application. So in most cases, when you're doing queuing or you're doing any type of load balancing decision, you usually want to do that on a per flow basis, not a per packet basis. Okay, it also means that when you're programming the flows in hardware, like to actually do the line card switching, if you were to do that on a per packet basis, it means it's going to be much more processor intensive to do that versus the individual flows. Okay, so this would be something analogous to like flow-based weighted fair queuing in your regular iOS platforms. You generally would want to do something like that versus doing like per packet classification or per packet load balancing. There's a question, when you set a port spanning tree type to network, does it have to be a Nexus at the other end, or can it be a 6500? It could be a regular port on the other end. The only difference is that whatever VLANs are not being received with BPDUs, those are the VLANs that are not going to be sent. So the advantage of this is that you don't necessarily need to do manual pruning of your trunk links with the switch port trunk allowed list command, because if the spanning tree port type is network, you're sending BPDUs bidirectionally ideally, the ones that you do not receive are going to be the ones that you stop actually forwarding on the link for the actual data plane. You will continue to send the BPDUs though. Question or comment, some equipment requires the same IP to appear on the same port like the 44 or 4 wireless controller, so you need to load balance by IP. There are some strange application requirements that you run into like that. We're going to talk about some of those within the scope of VPCs. There's some non-standard implementations of data center equipment like load balancers or certain of the storage arrays that use kind of proprietary features that go against the basic Ethernet standards, and then you end up in some weird traffic forwarding patterns. So based on your specific application, you may be limited to do one type of port channel load balancing method. But if we look at here on the CLI, notice here that this option is global. So if you have a particular application attached on a particular switch that you can only do IP load balancing, or you have to do MAC load balancing, it means it's going to affect all of the other channels that are on that particular platform. There's a question, can a port channel have a mix of F1 and M1 ports? I know in VPC it cannot. Statically, let's actually test that real quick. If we look at, let's look back at our topology here. Between the Nexus 7Ks, these are the M1 ports at the top, the pink ones. The F1 ports are the blue ones. Okay, so let's say we're going to channel all 4 of these links together. So let's go to 7K1, and let's show run interface E1/1 to 2, comma E2/1 to 2. Okay, I need to remove or at least add these configs to the other member interfaces. So let's say on these links, okay, everything is a switch port. They're all trunks, they're all network type, a spanning tree port type network. And then I'm going to shut them all down. I'm shutting down the physical member links. Same thing on the other side then. Let's say show run interface E1/9 to 10, comma E2/9 to 10. And I need to say the same thing. So these are, let's say, switch port, spanning tree port type network, switch port mode truck, and then I'm going to shut them down. Okay, so now let's aggregate them together. Let's say that this is going to be channel group, let's say 7 for the 7Ks. Channel group 7 mode active. And feature LACP needs to be on. No, we can't. So we'll see that there is a feature that runs behind the scenes that's known as the port channel consistency check for the compatibility parameters. That basically that's what it's saying, that the rate mode is not compatible. Basically, the physical links have different, or the physical cards in this case have different hardware requirements, so they're not allowed to channel in the same group. You would also see that if you took an F port and plugged it into an M port on the other side, so F1 on one side, M1 on the other side, and you were to configure a VPC, it will detect that through part of the Cisco Fabric Services protocol, the management protocol, and it's going to disable the channel. So in the vast majority of cases, you would plug M ports to M ports and F ports to F ports. Okay, there's a couple other questions. If the spanning tree port type is network and the port on the other side is root, it will not send BPDUs. Well, in rapid spanning tree, you send BPDUs regardless. You send BPDUs out all ports, so it should be fine. Worst case scenario, you could revert the link to spanning tree port type normal, which just means that you don't run the bridge assurance feature if you have some sort of interoperability problem with it. So spanning tree port type normal, that's the same as like a regular port in Catalyst iOS.